All right, hello everyone. Welcome. So today we are very happy to have Filippo Ascolani from Duke University, who has done a lot of great research in MCMC theory and other subjects. So today we will have his talk on coordinate-wise MCMC methods. Filippo, whenever you are ready.
Thank you very much, and thanks very much to Kian, Guanyang, Stefan, and Sam for inviting me, and thanks a lot for organizing this very nice seminar series. I have been enjoying that quite a lot. Actually, one of my recent projects on a non-reversible method actually started by looking at Gareth Roberts' presentation last spring. So very useful for me, and again, I am one of your YouTube followers and subscribers, so many thanks for this. So today I'm going to talk about coordinate-wise method, and in particular, so this is of course a very classical and well-studied topic. What I will focus on today is the results that we have been obtaining in the last few years for classes of distribution that are particularly relevant in Bayesian statistics. So in particular, the target distribution that are posterior distribution that are very structured or have some properties like log-concave. But before, let me acknowledge my co-authors, Hugo Lavenant from Bocconi University, Gareth Roberts from Warwick University, and Giacomo Zanella, again from Bocconi University, who is my long-standing collaborator. Even if he was not my PhD supervisor, he had been one of the people that impacted on me the most in the last few years. So I'm very grateful to work with him. Okay, so just the plan for the talk is to give you some background on sampling and coordinate-wise MCMC and why we think that in some situations it might be particularly competitive. And then we'll focus on a motivating example that is hierarchical models, both Gibbs sampler, so when we do exact sampling, and Metropolis-within-Gibbs, when we do invariant sampling from the full conditional. And in the final part of the talk, I will discuss log-concave distribution and Gibbs sample for log-concave distribution and application to various problems. So just some background that I think is very clear to everyone here. So the main goal is to sample from a possibly very high dimensional distribution that is here on RD. And the typical motivation is that X is a set of parameters, and we want to sample from the posterior distribution of the parameter given some observation. And the X can be again parameters, latent variables, and so on. There are many ways of doing that. In particular, if you consider a Markov chain Monte Carlo approach, there are two main classes of methods that are the gradient-based method like Mala or Hamiltonian Monte Carlo, where you kind of follow the gradient and you use local information, or the coordinate-wise method, where at each iteration you sample from one of the coordinates. So you can have Gibbs sampler when you do invariant sampling, or you have Metropolis-within-Gibbs when you can do exact updates. And today we will focus especially on coordinate-wise method, but we will make some connection and comparison with the gradient-based schemes. So in particular here, the main algorithm we'll consider is the Gibbs sampler. So we have a distribution on RT, and at every iteration we select at random one of the coordinates, and then we sample exactly from the full conditional. And in this way, we know that the resulting kernel is time variant. So here we focus on the random scan case, so we select one coordinate at random, but some of the results we show hold also for the deterministic scan. I will not discuss that in particular, but of course, feel free to ask me if you need any clarification. So here in the Gibbs sampler case, we assume that we are able to sample from this conditional distribution, but if we cannot, then there are the Metropolis-within-Gibbs case, where you sample from an operator that is invariant with respect to the conditional distribution. And this is what is called the Metropolis-within-Gibbs. So as a kind of a goal is that here a key point is that you are interested in the scalability of the method. So if Z become very large, how many iterations are needed to get to convergence and to approximately sample from the correct distribution. And there have been a lot of advances for gradient-based techniques there is still a lot to know, but we have a much sharp understanding, especially for large quantitative distribution like log-concave distribution. It has been a lot of work in the last decade. However, there are relatively less results for Gibbs type scheme, and argument and proof can be quite case specific. So the goal of this talk is to discuss some recent development where we look at complexity theory results for generic, hierarchical, and structured models. And also, we kind of have a general proof technique that allows to make some connection between exact update, that is the Gibbs sampling, and invariant update, that is the Metropolis-within-Gibbs. And finally, also to log-concave distribution. And as a kind of a motivating example, we consider the Bayesian hierarchical models that we consider broadly as the kind of target that arises when you combine simpler model in possibly very complex distribution. So in general, you have global parameters, less global parameter, up to local parameters. And then you combine those, and typically in this case, it is possible to have tractable subconditional. And this is a case where it is empirically well known that coordinate-wise methods can be quite efficient and possibly more efficient than state-of-the-art gradient-based sampler. This is, for example, the autocorrelation function. In blue, the Gibbs sampler, and in red, the Hamiltonian Monte Carlo for a high-dimensional hierarchical models. And so the kind of idea is that we expect in this kind of situation where we have some structure in the posterior to be able to competitively use coordinate-wise sampling. But to be a bit more formal, what we'll consider as a kind of posterior that will be amenable to coordinate-wise sampling is what we call a separable target distribution. So here, what we consider is cases where the logarithm of the target distribution can be decomposed in a separable component where each function depends on just one of the coordinates, and then you might have some interaction between pairs of parameters, and then finally a function that depends on a linear combination of all the parameters where the matrix A is sparse or very sparse. And it's a situation that is common in some Bayesian contexts like hierarchical models or generalized linear model, lasso, graphical models, and so on. And here the main concept is that the cost of updating a single coordinate is a fraction of the cost of evaluating the full posterior distribution. So this is a situation where you expect the Gibbs sampler to be competitive, and the idea is the following. So since coordinate-wise method updates one coordinate at the time, if you have a separable target that arises from any model, the cost of doing one Gibbs sweep, so the cost of updating all the coordinates with a Gibbs sampler, is essentially the same of evaluating the target distribution or the gradient of the target once. And it is the same kind of comparison that people do in optimization when they think that using coordinate-wise optimization can be better than using the full target. And here, these are exactly the case where we expect the coordinate-wise method to be competitive. And as a kind of a measure that we use to evaluate whether the coordinate-wise sampler is more competitive, we will look at a classical quantity that are the mixing time. So here we look at the number of iterations that are needed for the Markov chain with operator P to get close to the posterior distribution, here using the total variation. So essentially, this measures the number of iterations that are needed to get convergence to the stationary distribution when you start from some classes of initial distribution n. And in particular, this class of distribution will be the class of warm start, that essentially means the class of distribution that are not too far from the target distribution. But luckily, in all the cases that I will discuss later on, we will be able to find what are called the feasible starting distribution, so distributions that are not very far from the target, but still you can actually sample from it. So I will not stress that a lot, but again, let me know if you have any question on the specific case. So let's start with a class of hierarchical model now, also to give you an idea of what to expect what's affecting those kind of situations. So this is the main general framework. So we have this graphical model. We have that each observation yj depends on some local parameters theta j that have some prior distribution that depend on some global hyperparameter psi that are the so-called global parameters. So here you have a clear distinction between global and local parameters. And the key point is that conditional on the global parameter, you have independence between the local one, also a posteriori. So this is a case where it is very natural to consider this metropolis within Gibbs scheme, where you sample the global parameter given the local one, and the local given the global, since it will be independent update. And here, since we are interested in a kind of a high dimensional situation, we consider the case where the number of groups that we call J increases. So we increase the number of local parameters and the number of groups. So essentially, we have that the number of data points and the number of parameters grows proportionally one to the other. And so here, actually, we do have empirical evidence that coordinate-wise sampling works very competitively. So just to give you an example, here we consider a toy situation where we have a logistic hierarchical model, where we have the global parameters that are global mean and variance, and then we have local parameters that are not normally distributed, and then we have the likely to be a Bernoulli with a logic transform parameter. And here we consider 10 observations per group, and the number of groups going to plus infinity. So if we look at the integrated correlation time, as the number of groups goes to plus infinity for different methods, what we observe is that the integrated autocorrelation time for Gibbs and Metropolis within Gibbs, so the coordinate-wise sampler, are very stable and do not seem to increase with the number of groups. While if you look at optimally tuned Mala and Emerson and Monte Carlo, we have an increase of the cost, and this is also on the log scale. So essentially, this seems to suggest two things. The first one is that coordinate-wise sampling seems to be robust to the number of the groups, in the sense that there is no apparent increase in the number of iterations. Of course, the cost per iteration will increase, but the number of iterations seem not to increase. And moreover, it seems that there is not really a big difference between Gibbs and Metropolis within Gibbs. We have that the Gibbs is slightly better, as we would expect, but not that there is a very big difference. So this is empirical evidence, and we would like to transform that into a kind of a formal result. And so the idea is to consider the following framework. So we take essentially a generic likelihood S, but the prior for the local parameter, we take it as belonging to the exponential family, like the normal distribution. And here, the main idea for that is that now since you are in the exponential family, we have 6-dimensional sufficient statistics. So if you look at the conditional distribution of the global parameter given the local one, so the update for this parameter given all the local parameters, this does not depend on all the parameter theta j, but just on the sufficient statistic. This does not mean that the whole model depends on just the sufficient statistic, but the update of the global given the local one. And the idea is that we don't want to work with a vector of local parameters that is increasing in dimensionality, since we want to make a limit at j goes to plus infinity, but we just want to work with the set of fixed sufficient statistics. And luckily, we can actually work just on that. And indeed, we have a formal result that says, if you look at the Gibbs sampler on global and local parameters, actually, you can also look at just the chain that looks at the global parameters and the sufficient statistics. This is again a Markov chain. And it is exactly the Markov chain that is the Gibbs sampler on global parameters and the sufficient statistics. And this is good because it is now a Gibbs sampler of fixed dimensionality. And now we can look at the number of groups going to plus infinity. And luckily, we can characterize the limiting distribution of the global and the sufficient statistics, and we can And actually, this limiting distribution turned out to be Gaussian, and so we can look at the Gibbs sampler on the limiting distribution. But let me stress that here, this idea of looking at the distribution statistic is not something that we can apply in practice in most of the case. So we cannot implement this Gibbs sampler. We just use it as a tool to study the original Gibbs sampler that you actually know how to implement. And combining all of these, we have our first formal result that says that if you have a well-specified model and you have some regularity assumption that allow you to have a well-defined limiting distribution for your model, then you have that the mixing times are order 1 as the number of groups go to +. So essentially, this shows that the mixing times are bounded with respect to the number of groups. So this is essentially what we call the dimension-free convergence. Of course, the cost per iteration will increase. So actually combining all of these, it means that the overall cost will be linear in J. So before we just saw the median of the autocorrelation time, but actually here we have a stronger result that tells you that everything is bounded in probability. And so we can look at, for example, at also the quantiles of the mixing time. Here we have the hierarchical linear model with a non-covariance, and here we have the hierarchical binomial model. And so in both cases, you see that both the median and the quantiles, and essentially the whole distribution, is actually over there. So this kind of explained the previous picture, but just for the Gibbs sampler. And now the question becomes how much of that actually depends on the fact that we were using exact update instead of invariant update. And so this is a very natural question, I would say. And also the problem becomes more difficult because we have some tools to study the Gibbs sampler. There are the drift minorization, orthogonal decomposition. So there are very sharp results for specific distribution, like for example, the Gaussian. And there is asymptotic analysis as the one we have already discussed. But it is kind of not easy to translate them for coordinate-wise schemes, but some recent results, like the one from Kian and co-authors, Kian, Guan, and co-authors in 2023. And so the idea here is to look at the difference between the Gibbs sampler and the Metropolis-within-Gibbs, and hopefully see that if your invariant update is not too bad, then there shouldn't be too much of a difference. And the way of formalizing that we use is to look at the conductance. That is a common tool to study MCMC convergence, and this is a number between 0 and 1. And the higher the better, in the sense that the higher this number means the higher is the probability that your chain moves fast. And indeed, what you have is that if the conductance is strictly bigger than 0, then you have exponentially fast convergence. And the intuition is that this number is essentially the probability of getting out of the set A if you start from the set A. So if the conductance is very small, it means that there are some sets for which it is very difficult for the algorithm to get out, and so it is possible that you get stuck. If this number is large, it means that your chain moves very fast and can explore the whole space. And now, what we want to do is try to connect the conductance of the Gibbs sampler and the conductance of the Metropolis-within-Gibbs. And this is the main result. So if you look at the conductance for the Metropolis-within-Gibbs, it is smaller than the conductance of the Gibbs. And this is kind of effective in the sense that you expect exact update to be better than conditional update, than invariant update, if you have the same structure, of course. But also, what we have is a lower bound that tells you that the conductance of the Metropolis-within-Gibbs is bigger or equal than the conductance of the Gibbs times another term that essentially measure how good are your conditional updates. So you look at the infimum over all the possible coordinates and all the possible starting points, and you look at the conductance of the coordinate-wise operator. So if these approximate very well sampling from the conditional distribution, then this number and this number will not be too much different. And so essentially, this essentially show you that the Gibbs always mixes pattern. And also, I think that is very interesting to me is that here, if you have multiple coordinates for which you can do exact sampling, you are just paying the price for the worth of that. And so essentially, you are not accumulating the error. Moreover, we have a very nice decomposition because it means that the conductance of the Metropolis-within-Gibbs is given by these terms here that essentially measure how good is the goodness of the coordinate-wise structure in general, and then a term that tells you how well you are approximating the specific conditional update. And I refer you to the recent work by Kian that essentially consider a classes of results of similar spirit and unify them and extend them. It is very interesting. I think there has been a lot of connection between different results of the same type. Also, let me stress that this result is tight in the sense that you can find examples with this inequality. And moreover, we can extend it to the approximate conductance, where approximate means that here you don't really have to compute this for all the axes, but you can just look at the axes that have high probability under the target distribution. And this is very helpful in a Bayesian concept because essentially you can exclude the tails if the tails are not that important. So coming back to our hierarchical context, essentially we have to show two things to show that the Metropolis-within-Gibbs is doing well. So the first one, we need to have that the Gibbs sample is well behaved, and this is exactly what we showed before. And moreover, we need to check that the conditional updates are good enough. So essentially, we need to show that this term is not too small. And in our context, this just means that if you look at the neighborhood of the true parameters, since you're looking at a well-specified model, then the update in a neighborhood of this parameter, and this neighborhood can be as small as desired, this minimum must be strictly bigger than 0. And in some situations, this is actually not very difficult to prove. For example, if you are in a binomial model. So essentially, we just need that the conditional updates are good around the value of the true parameter, since your posterior will be very concentrated around that. So again, we have a similar result as before. And again, we need to ask for the model to be well specified. We need to have some regularity, and also that we have a control for the conditional update. And also in this context, we have that the mixing times are bounded as j goes to plus infinity. And actually, we can find something that is essentially our warm start with j log j cost. So essentially, we have that the total cost is given by j times log j. And this compares to gradient-based method that typically require to have a power of j with degree bigger than 1. So let me stress that here a key point for me is that you don't need just to check this part. That is something that we have already seen in the previous part, but also how well you are approximating the conditional update. And in practice, this can have a great impact. So let me show empirically this thing. So if you look at a hierarchical logistic regression, so essentially the same thing as before, but now we have some covariates. And if you look at the integrated autocorrelation time as we increase the number of covariates per group. So here the conditional update becomes more and more difficult. And so here we have all samplers with the same coordinate-wise structure, but we use different metropolis steps. So the lower line corresponds to the Gibbs sampler, and this increases very slowly with the number of covariates. While if you take worse and worse samplers, you see that there is a huge increase in the integrated autocorrelation time. And in particular, this one corresponds to the independent metropolis testing that it is well known to become worse and very fast if the dimension is reduced. So essentially, this shows the impact of how well you are approximating the conditional update. So I think that that is very nice for me that you can separate how good is the coordinate-wise structure with how well you are approximating the ideal. So this was for the hierarchical models, but now let's consider another class of distribution that is very well studied in the MCMC literature, that is the class of log-concave distribution. And so here we will also try to make a comparison with optimization and gradient-based method. So log-concavity is a very well-known property that essentially asks that the target distribution can be written as the exponential of -u, where u is a m-convex and L-smooth function, meaning essentially that when you iterate differentiable, you can upper and lower bound the action. So essentially, you can find two Gaussian distribution upper and lower bounding, essentially. And this is a very canonical setup for theory, and it's essentially the same as studying convex optimization, convex function for optimization. So it is a kind of class that we use to assess the convergence properties of different algorithms, and this has been studied a lot for gradient-based samplers. However, up to the recent year, there are almost no results for coordinate-wise method, and this kind of makes sense because the gradient-based methods are local, so it is kind of possibly more intuitive to how to exploit this information, and it is less clear, I would say, for coordinate-wise methods, since at every iteration you can make a very big step. And so now the question is, can we say something about Gibbs sample for log-concave distribution? Let me just restate just for a second the Gibbs sample, just to fix the notation again. So here we have our pi that will be log-concave, and then we focus on the random scan case, and here we need and here our result hold for the random scan case. And we sample at each iteration one coordinate, and then we sample from the corresponding full condition. So the main result that we have is the following: if PGS is the operator of the Gibbs sampler, and we call new PGS the operator, the chain started from the starting distribution mu, then our main result is that if you have the target distribution that is log-concave with and u is m-convex and L-smooth, and we call kappa the condition number, that is the smoothness constant over the convexity constant, then the contraction rate that we have is 1 minus 1 over kappa times delta times t. And this d is very reasonable since we are just updating one coordinate or one block at a time. So this nicely holds for every starting distribution mu, and the contraction rates here depend only on the dimension and on the condition number. So let me just give very briefly the implication. So this result actually tells us that after any iteration, we have that the distance in Kullback-Leibler is given by the same constant to the power of n. That means that if we want a KL that is more than epsilon, we need at least k times d iteration. But actually here, a single iteration just moves one coordinate. So in general, especially if we have a separable target, essentially this means that the Gibbs sampler requires order kappa full target evaluation to achieve epsilon error. Here we consider the Kullback-Leibler since it is more convenient for our technique, but actually this is stronger than total variation and versus time distance. So actually this translates to having results for those distances as well. So again, if the cost of performing a single coordinate update is 1 over the cost of doing a full target update or evaluation, then essentially this means that we have order k iteration needed to achieve epsilon error. So this is essentially the computational cost that depends only on the condition number and not on the dimension of the distribution, of the dimension of the target distribution. However, there is an issue here that the condition number may not be a very reasonable quantity to look at if you study the convergence of the Gibbs sample. And for two reasons, actually. The first one is that the Gibbs sample is invariant to rescaling of the coordinate, essentially because you're doing exact updates. So if you take something like this, where you have a product measure, but with the scale of the two, but with the scale of the two coordinates to be very different. Here, the condition number is very big. But if you actually rescale the coordinate to be of the same scale, you have the condition number to be equal to 1. So they have very different condition number, but the Gibbs sampler perform in the same exact way. And actually here it is very good. So from this, you can see that the Gibbs sample is invariant with respect to the rescaling of the coordinate, but the condition number is not. And moreover, there is a kind of the opposite issue that is essentially that the condition number measure how anisotropic is your target distribution and is invariant with respect to rotation. But actually, the Gibbs sampler is very much not invariant to rotation. If we change the orthogonal basis, you can completely change the properties of the algorithm. So here, the condition number seems not to be exactly the correct number to look at. So in order to at least partially fix this problem, what we do is to consider a kind of a coordinate-wise condition number that is essentially that essentially resolve at least the first issue. And the thing that we do is essentially to rescale our potential with the smoothness constant for every block. And then in this way, essentially, it means that if we have this scale here, now in the new rescale distribution, we have that all the lengths here are equal to 1. And now you can look at just the convexity constant. So essentially, we are rescaling the distribution, and now we just look at the convexity constant. And essentially, if you consider a Gaussian case, it means that you're just looking at the correlation metric instead of looking at the covariance metric. And actually, it can be proven that this new coordinate-wise condition number that we call K star is always smaller than K. So this actually leads to a tighter bound. And what we have is that we can replace in our theorem K with K star. So actually, K star tells you what is the number of full target evaluation that you expect to make with a Gibbs sampler. And notice that this is something that has been already looked in the optimization context by Nesterov when he studied coordinate-wise optimization in a kind of a very similar context. So for example, so now the question is this result tight? So does it make sense that this is the correct dependence on K star? It makes sense that it could make sense that it is the correct dependence on D, but one wonder whether it is correct dependence on K star. And it actually turns out to be true. Indeed, if you look at the Gaussian case, so here everything depends on the covariance matrix. And since you are rescaling everything, you just need to look at the eigenvalues of the correlation matrix. And here it is known from other techniques that the contraction rate is at most 1 minus 2 over K star times T. So essentially, up to a factor of 2, we have a tight result. So this is actually the correct dependence, at least in the worst case. So here it is nice to make a connection with coordinate descent, or because here essentially we are doing something that is really the analog of that. So if in the Gibbs sampler we sample from the full conditional distribution, in the coordinate descent, at every iteration we minimize over one of the coordinates. However, there is also another algorithm that is in a way in between those two, that is the CAVI, the coordinate ascent variational inference, where you want to approximate your your target with a product of the distribution. And so here, at every iteration, you minimize according to that specific coordinate. So again, those are all algorithms that somehow at every iteration just look at one of the coordinates. And here, what it is very nice to see is that the convergence rate of the three algorithms are all exactly the same. So there have been, so starting from Nesterov, that is the original result for the optimization, but also those two papers for the CAVI, and finally ours for the Gibbs template. Essentially, the rate of convergence is the same regardless of the specific problem you're looking at, like either optimization, either approximation with CAVI, either Gibbs template. So here there is no gap between sampling and optimization. And notice that in general, this is not the same for gradient-based method. Indeed, for gradient-based method, when you do sampling, since you have to discretize somehow, then you're paying a price for either adjusting with a metropolis step or either to have a very small discretization to avoid too much bias on the target distribution. So if you look at the rate of convergence for optimization and sampling using gradient-based method, you will have a factor more in the sampling case to account for the discretization. Moreover, let me stress that even if CAVI, I mean, even if they seem to be be similar, actually there are a lot of difference between those three problems. And first of all, the first thing is that coordinate descent and CAVI operate in the product space. So in the coordinate descent, you look at the RD. For CAVI, you look at the product of the distribution on R, while the Gibbs sampler is not an optimization on a product space. So essentially, you have the same rate of convergence, but the techniques are very different. I will not talk a lot about the proof techniques here, but let me just stress that it is very different from the usual one for gradient-based schemes that are very well developed. But while for gradient-based, people tend to work with a discretization of the continuous time in Langevin dynamics. Here we need a different approach that is non-local. Since at every iteration we are going to move in a single coordinate, possibly very far from the initial point. So here the idea is that if you look at the PGS as the average of PI, where PI is the operator that updates the ith coordinate or the ith block. Here, if you have the convexity of the Kullback-Leibler divergence, you have that the distance between one iteration of the Gibbs sampler and the target is more or equal than the average of the difference when you update just the ith coordinate. And now we can use a kind of a variational property of PI, since PI does exact sampling. And so if you look at the distance between your distribution mu and pi, you can decompose it using the property of the Kullback-Leibler distribution. And so you have the distance between the distance between the marginal over all the other coordinates. And then you have the distance between your update, the distribution of your update on the ith coordinate, and the full conditional. But actually, since we are doing exact update, this becomes 0. So essentially, we just need to work with the average of these Kullback-Leibler divergence, that is the distance for every distribution marginalizing over the ith coordinate and showing and connecting to the full Kullback-Leibler divergence. And here, and actually, this is the main result that we show, that is often sometimes called the approximate tensorization of the answer. So this is the main thing that we prove in the paper using optimal transform technique. And actually, this implies similar results for the variance, for example. So we can, so essentially we're looking at the connection between the variance of f of x and the average of the expected variance conditional on every block. But actually, so here I'm not discussing much more on the proof technique. You can find more details on our archive. But let me, so here, this regards the Gibbs sampling, but I think that it's nice to understand when we expect the Gibbs sampler to be kind of better with respect to gradient basically. So first of all, we need to have separable targets for this to make sense, because of course, if the cost of updating a single coordinate is the same cost as doing a full target evaluation, so we don't expect the Gibbs sampler to work well. But also, in those situations, for different means, we have different dependence on the condition number and the dimension. So here we compare some of the state-of-the-art bounds for different algorithms. So we have that the Gibbs sampler, both with warm star and feasible star, the number of full target evaluation is given by essentially by the condition number with no dependence on D. While for all the other gradient-based methods, we have a combination, we have a product of two things. That is the product of the condition number that essentially tells you how much this depends on the geometry of the space, and the cost that depends on D that essentially measure how much the discretization impacts the result. And it is nice to notice that, for example, for the Hamiltonian Monte Carlo, depending on the specific assumption, you can have a dependence that is smaller than k and can be also square root of k. So actually, from this, what we expect is that the Gibbs sampler should be more robust if you let D increase and you have a geometry that is not too bad in the sense that the condition number is not too big. Instead, Hamiltonian Monte Carlo seem to be more robust if the condition number is high, but can suffer if the dimension is very high. And also, this is confirmed by some empirical evidence. This comes from a very nice recent paper that essentially tries to compare Gibbs sampler and Hamiltonian Monte Carlo for generalized linear model. And here you see that when the dimension is kind of smaller, then the Gibbs sampler is more expensive, but as D grows, you have that Hamiltonian Monte Carlo deteriorates faster. So those were the basic results, but actually we also have some extensions and applications. So the first thing that is that actually we can go a little bit beyond our result. And if we have a target that is strongly log-concave, but we also have a separable part that is the product of functions that are, and those functions only need to be convex and not necessarily strongly convex, then essentially we have the same result. So if you have a situation of this case, and this is what we call the separable part, you still have a cost that grows linearly with kappa star that is the condition number for you. And just to give you an idea of why this could be useful in a Bayesian statistic context, let me briefly discuss the case of probit regression. So here we have that you have different data point yi, but now the link between the regression coefficient and y is given by the probit link. And this is an example of a generalized linear model. So here, a very classical way of constructing MCMC samples for this is to look at a suitable data augmentation that takes back to Albert and Chip. So here you introduce some latent variable Zi that depend on just on the regression coefficient, and then your yi will just be essentially given by the sign of the Zi. So essentially now the regression coefficient becomes the global parameter, and this new variable Zi to be the local one. And here, this this is absolutely equivalent to the previous formulation. And now the conditional distribution of beta and theta becomes available, and we can construct a Gibbs sample. And the Gibbs sample here, it is very easy because you just update all the Z from a truncated normal distribution and all the beta from a multivariate normal. And the nice thing is that if you look at the posterior of the expanded variable, so Z and beta, you can rewrite that as a multivariate normal times some expression that essentially are just indicator functions that are log-concave functions. So essentially our theory tells that we can ignore this second part. And so this is what we call the separable part. And we just need to look at the K star for the multivariate normal case, that is of course much easier. So exploiting this extension, what we have is that the mixing times or the data of the data argumentation scheme is given by this expression that is very neat and without any hidden constant. And so essentially everything depends on the maximum eigenvalue of x times the precision matrix x transpose. And notice that is very similar to a result that has been obtained by this very nice paper that uses completely different proof techniques using log isoperimetric inequalities. Notice that these bounds hold uniformly over all the possible realization, and they hold for every n x tends to 0. So it is not an asymptotic upper bound, but it's really non-asymptotic. And this is also a case where the best bound for gradient-based method grows at least as square root of t. And just let me add that that a very similar bound holds for the collapse Gibbs sample that just look at that variable. But actually, if you want more details, you can look at our preprint. And the nice idea about this is that now we can look at different asymptotic regime and see what happens. So for example, if we have a G prior that is known to be in this form, then it means that the Gibbs sample will be always, then the mixing time will be always upper bounded by 2 plus G. Or for example, if you look at random covariates and diagonal precision, then we have the following following up now. So here, if n over d, if the number of observations over the number of covariates goes to a fixed constant, we again have small mixing time in high dimension. And just to give you a very small visualization here, we look at the total variation distance estimated by different coupling techniques using different cases. So here we see that even if we include both n and p, the total variation distance at a fixed number of iterations remain more or less the same. So finally, we would have other extension that I will not discuss today, since I think I am very close to finishing my time. We also have some extension to the hit and run algorithm. So just let me conclude by saying that here we look at the Gibbs sample for structured target distribution, and essentially we show that in those situations the Gibbs sample can be very competitive. But let me stress that I'm not saying that the Gibbs sample is always the best thing to do. Actually, there are many situations where you don't have a structure or you don't know anything about your target distribution. And so in that case, the Gibbs sample could be actually much worse than, for example, Hamilton and Monte Carlo. So the main takeaway is not that you should always use the Gibbs sample, but that there are some situations where you can exploit the structure of your target distribution to develop a good coordinate-wise scheme. And again, there are many big open questions. So we would like to apply to specific the Bayesian model. Here I have presented the probability regression, but there are much more. And then there are two very big questions. That is, can we go beyond log concavity? For example, we have a spike in the lab or something like that. And also here we have that the dependence is always at best linear in the condition number. And then the question is, can we accelerate this somehow to get a better dependence? And here there are some result for the gradient-based scheme, very recent by Hardschuler, Chiwi, and Tang for the underdamped Langevin dynamic. So this is it, and thank you very much for having me.